All right, so good evening. Thanks for coming. So as Claudia mentioned, I'm Thomas Cullen, and my talk's on Antarctica's ecosystems and how they've changed through time compared to how they are today. So just to refresh everyone's memory, here's Antarctica. And as Claudia mentioned, we were in the peninsula only. So we're talking about a really massive landmass here. And we are only really just seeing tip of the iceberg, so to speak. Yeah. Anyway, so first thing I just want to direct your attention to is on your right, this little diagram. This is just showing sort of what keeps the modern Antarctic the way it is, or at least has a major impact on it. And this is the Antarctic Circumpolar Current. And what this is extremely large current system of both air and water that sort of rotates all this material around the Antarctic continent and prevents any of that warm, low latitude temperatures and air and whatnot from penetrating into the continent. And it helps to keep it thermally isolated and cold. So here's just a few shots of Antarctica today. So this is a common scene. You'd see down there, this is Seymour Island, which is what Claudia alluded to. This is the island that, as the geologists, we specifically begged them to bring us to, and I'll keep you in suspense for a little bit longer as to why that was. But, so what you're seeing down there, a lot of it is this sort of barren, desolate sort of landscape, really breathtaking, but at the same time, a little bit bleak. And you're seeing lots of ice and snow. And just to get an idea of the scale, that in the center there, that's a Zodiac, the sort of inflatable vehicles we're using to get from the ship to the land. And that's, I think, 14, 16 feet long. So those are some pretty big pieces of ice. And then it's another shot, a typical sort of scene we'd get down there. This is at Brown Bluff on the Antarctic continent itself, as opposed to Seymour, which is an island just off. And so again, huge mountains, glaciers, sort of barren ground. Keep in mind, very, very little vegetation, and lots of animals like this, little penguins and fur seals. And we'd see so many of them that it's another penguin, so pretty spoiled. But this is sort of what I want to get to the meat of the talk, and this looks a little bit daunting. This is a view of the food web of today in Antarctica. It's actually a little bit simplified from the real one. So it gives you an idea of how complicated some of these ecological things are. But like all ecosystems, it starts out with the sun, primary production. The sun gets light, and then the producers, like phytoplankton and ice algae, they will photosynthesize and grow, and they're eaten by primary consumers like krill or zooplankton. And so krill is really what I want to focus on here, because if you sort of follow the lines out from there in their little convoluted pathways, they all sort of link up with krill. Everything else on this chart that's above krill in the order eats krill or eats something that eats krill. And for a whole ecosystem to be dependent on this one sort of keystone species makes it very vulnerable, but also it shows just how dependent on marine conditions this ecosystem is. So if you think of other ecosystems today, like maybe around Ottawa, you're getting a lot of terrestrial things, so herbivores eating grass, carnivores eating them, etc. You don't have everything being 100% dependent on the sea, and but that is what you're seeing here, because there's just not a lot growing on land. And to sort of drive that in a bit further, here is a bit of grass from Antarctica that we saw growing there, and nothing really eats it. There's no deer, there's nothing like that. Everything's living off the sea. And this stuff here is not even doing very well. You can see it's all sort of dead there. So it just sort of ekes out an existence. And part of this today is that since Antarctica is so desolate, so covered in ice, the only way to get to Antarctica is if you swim or you fly. Or you can tag along with something that does, which is probably how the grass got there. But contrast that, the past, because Antarctica was not always where it is today, and it wasn't always like it is today. So first, to just preface this, at the top right, you have just a little cartoon diagram there explaining sort of continental drift. So continents on tectonic plates. They shift around in relation to one another. And so as a result, the continent position is not fixed. So here it's just showing Australia, Antarctica, Africa, and South America, and just sort of how they're gradationally changing over time. And so if you take all of that back into the deep past, say 250 million years ago, for example, you have all the continents smushed together into this large supercontinent, which is called Pangaea. And if you go a bit further after that, that continent starts breaking apart, and you get what's seen up in the top left, which is in the late Jurassic, 152 million years ago. And so here you can see continents are no longer totally together. They're breaking up a little. But you have all of the southern continents still fused together as a sort of supercontinent that was called Gondwana. And so from that, you can see like Antarctica, Australia, India, Africa, South America, all stuck together. Track that forward to the Cretaceous-Tertiary boundary, about 65, 66 million years ago. Things were broken up a bit more like today, but Australia, Antarctica, and South America are still hooked together. So that circumpolar current I talked about, it isn't there yet. And another thing to keep in mind here is you're not really seeing much in the way of polar ice in these times. And you're not seeing, as a result, you're seeing much higher sea levels. So if you look on the top, a lot of Europe and Asia is sort of inundated with this water. And you look in the bottom, Asia, Europe, North America, Africa, they're all sort of got these shallow inland seas. So that's where all the water went. And then you fast forward to today, and you get the map you recognize. So when you go back to these sites, such as in Antarctica, you look at the fossils, you find some interesting things. But before that, there's some effects that this sort of lack of ice, this warmer world, has on animal and plant communities. And the general gist of that is that when the Earth warms, temperature gradients go they become less pronounced. So you see a drop in the isolation of different animal groups. So here's just some little graph here. It's a bit busy, but you can see in the red line, that's from about 50 million years ago, the purple 4 million years ago, and then the blue is today. So this is showing mean annual temperature on the y-axis and latitude on the x-axis. So on the far left, that's the South Pole, far right, North Pole, and 0, that's the equator. And so you're seeing just the difference in temperature when it's much, much warmer than today, such as it was 50 million years ago. And look in the difference in temperature between the poles and the equator, and then compare that with what it is today. It's much steeper. So the average difference in temperature between the poles and the equator 50 million years ago was about 25 degrees Celsius. 4 million years ago, 30 degrees Celsius. Today, it's around or over 45 degrees Celsius. And why that's significant is because when you have these less pronounced gradients, the terrestrial biodiversity at the poles becomes much increased. And this is shown in the fossil record. So these are reconstructions, all based on material from Antarctica or southern Australia. And remember, southern Australia was about the same position as Antarctica and connected to it at the time. So here you're seeing diverse terrestrial animal communities, dinosaurs in this case, based on the age of the material, plants, all kinds of stuff. There's still probably a bit of snow, and it would still be dark for quite a few months of the year, but it was very different than it is today.